Good evening, everyone. It's a real pleasure to be here. What I'd like to do today is bring you on a journey engineering swarms across scales and applications. And the science of swarm robotics has been around for around 20 years. What got us excited in the area of swarm engineering is this flock of birds and its ability to do beautiful, complex dances in the sky. There's many features in this flock that are interesting for real-world applications. For example, if you keep adding birds to the flock continues to fly, and so it can scale to huge numbers. If a bird falls to the ground, the whole flock doesn't crash, and so it's robust to individual failures. And together it can do more than the sum of its parts. For example, it might be better at avoiding predators as a collective. Now, what's fascinating is that these patterns in the sky are not the result of one leader bird telling every bird what to do, but rather the result of every bird reacting to the local world around it, following perhaps a simple set of rules. And if every bird in that flock follows those rules, you get these beautiful murmurations. This is what we call emergence and also self-organization. Now, we see examples of swarming or self-organization everywhere around us in nature, whether it's this flock of birds, or these ants as they create trails to your picnic table, or bees as they make decisions about their next nest site, or indeed our ability to grow functional shapes just from a couple cells within the human body. So why is it so challenging to understand or indeed to engineer swarms? Well, we have a challenging puzzle to crack. Very often we'll see a collective behavior, a flock, a trail, a decision-making process, a shape, but we won't know how to design the individual agents and their rules, their local interactions, to give you that desired swarm behavior. Just like if you were to take a bird from that flock and look at it, that wouldn't explain how the flocking happened. And so we have different tools to be able to engineer swarms. One tool is bioinspiration. Biologists have been studying the birds, the ants, the bees, the cells for a while, and we can use some of their rules, simplify them, and put them on artificial systems like robots, and hopefully we get similar behaviors. Here's an example from 15 years ago when I was a PhD student, and I was interested in adopting the rules of flocking on a swarm of flying robots. So these are the rules that my flying robots followed. In the middle, you have a flying robot. It can only sense the robots around it, so there's two within that gray area. And that flying robot is attracted to other robots within that area. It's also pushed away from those robots, because otherwise they would all crash. It tries to align or points in the same direction as its neighboring robots. And then finally, it would like to go to a certain position, this migration point. So it has these four forces pulling on it, four rules, and you add them all together, and that tells the robot where it should go. And if every one of the robots in that flock follow those rules, what you get is a simple program that you can put on a flying robot. So I programmed these robots, my colleague threw them in the air, and then what we'd predicted using simulation is that their dance would end up being a circle. And here you see it after a certain amount of time converge to this circle. And these dots that you are seeing are the GPS trajectories of the robots in the air. So we can take rules from the biologists, put them on flying robots, throw them in the air, and they give us the predicted swarm behavior. In a similar way, we can put rules on simple robots and have them create trails, a little bit like the ants that you saw before. So here we're releasing these coin-sized robots that we have in the lab. We have around 1,000 of them, and each one of these robots can sense within 10 centimeters around it other robots. It can shine a different light pattern so we can see what state it's in, and it can just buzz around, move in a more or less controlled manner. But we can take some of these rules, put them on the robot, and create trails. Inspired from bees, we can have these robots here, there's 400 of them, reach decisions. So you can see here they're deciding between blue and red. So in this video, they start half and half blue and red, and then in just 4 minutes, through simple local exchanges of information, simple motions, all the robots turn blue. And this is directly inspired from how bees do waggle dances in the nest to tell other bees where to go. And in this setting, we're inspired from tissue and how in biology, and during embryogenesis, you're able to grow functional shapes in the body. And so what we're doing with our swarm here, now we have 300 of these coin-sized robots, is pretending each one of these robots is a cell. So let's call it a robot cell. And the swarm as a whole is a robot tissue. And this is work with biologist James Sharp, who studied how to do this in biology. And each one of these robots has two chemicals, U and V. They're not real chemicals, they're just numbers in the memory of the robot. And these chemicals react with each other. So U will create itself and create V. V depletes itself and depletes U. And this is what we call a reaction network. So these are basically numbers on each robot cell going up and down. And then we also send these numbers to neighboring robots, which is a process of diffusion. And this together is called reaction diffusion. And this equation was actually described by Alan Turing to describe how spots and stripes end up on the skin of animals. And it turns out if you run this on a robotic tissue, what do you see emerge? Spots. And depending on the numbers you put in, you actually see stripes and other patterns. Now, in our robot tissues, we can't kill or multiply robots just yet. And so what we're doing is moving them from areas where they should die in that robot tissue to areas where they should grow. And through this process, it takes about 3 hours, but our robots take 10 minutes to get patterns, and then we see these protrusions grow a little bit like the digits that form in biology. And these protrusions, which we're thinking of as little limbs, we can control them in different ways, and they're very robust because of this self-organization. So for example, here you see them start and then they grow these protrusions. Turns out that if you chop off some of these protrusions, they regrow. And actually it depends. If you chop them off too much, then you redistribute the cells to other area of the swarm. And you can also split the swarm and it self-heals. And in the process of self-healing, these spots move and then other limbed structures emerge. So this was just a taste of some of the science of it. And this is looking at how biology inspired some of these controllers, especially with these simpler types of robots. But there's another tool that we now have to design robot swarms, and that is automatic exploration. So you can imagine there's many engineering applications where biology hasn't yet told us what the right way to design our swarm is. And in those cases, sometimes I guess as a swarm engineer, so I'm programming the robots, I'm looking at what happens, and then I keep changing it. Or sometimes, and increasingly so, we use machine learning to automatically explore the right programs for our robots that give rise to desired swarm behaviors. And let me just give you a taster for how this works. This is also inspired from biology. It's called artificial evolution, and this is what we use to automatically design programs for our robots. How does it work? Well, let's say you want to achieve a swarm task, like flocking. And let's say you don't know how to design the robot program. What you could do is generate lots of random programs. That's what I'm showing here. And this is what we call generation 0. So at the start of evolution. It's all done in computer programs, obviously. And so what we see here is that to test these programs, we'll take the first program, copy it on every robot in that flock, test it on a flocking task, and measure how good it was at doing that task. So for example, we might give it a score of 25. You then go and test every one of those programs within your first generation. And what you see is pretty much, you're pretty bad usually, bad scores. And that's because everything is quite random at this stage. But you have some of these that perform better than others. And so you select these, inspired from natural evolution, to reproduce into a new generation of artificial robot programs. So let's say we take the best scoring programs here, and then what we want to do is mix them. The idea is if two good programs mix together, maybe they make a better program. And so you'll mix your programs together, that's called crossover. And then you'll add a little bit of randomness through mutation, although it's all artificial mutation. And then again, you go and test them on the swarm behaviors. That's a new generation of robot controllers. You give it a score. And the idea is that over many generations, let's say 50 or 100, you go and improve the programs for your robots. For example, now we have much better scoring robots. And probably we would adopt the one that has a score of 90, and that will be the program that we then use to deploy our robot swarms. So what does this look like in reality? Here you're looking at a swarm of robots. They're a little more sophisticated than the ones you saw here. They now have GPUs on board, so they have more computation, and they are running artificial evolution on board every robot, which allows them to learn on the go how to behave. In this case, their goal is to push the frisbee to one side of the arena. And when they start, they're a bit messy, you can see that here. But over time, they get better and better at pushing this frisbee. In fact, it only takes 15 minutes in real-world time for these robots to go from not knowing how to behave as a collective to being better at it. Now, one thing that we care about when we're evolving these swarm behaviors is that we can look into the brain of the robot and understand what it's come up with. And so that tree on the left is actually the program of our robot. It's called a behavior tree, and it's what the gaming industry uses to program little characters in games. And so it's something that we as the engineers can look at, can read, can color code, we can make sense of it. And so that allows us to have confidence in what the swarm came up with and even adapt it to new robots or new behaviors, because we can peer in to the brain of the robot in a human understandable way. Another tool that we have, which is quite new, is to be able to look at videos of swarm behaviors, be it robot swarming or natural, which we're just trying now. And the idea is if we look at the swarm, can we automatically, using again artificial evolution, extract the rules? So this is like an automatic swarm engineer. And the hope is that this will allow us to explain these natural swarm behaviors, translate them to artificial systems like robots, and maybe control them. So as an example, what you're looking at here on the left is a swarm behavior where we produced one video. So all we need is one video of that swarm behavior. And on the right, after our automatic extraction method, we end up with the same behavior tree, just as the original one, without needing to know very much about our environment. So we're now at a stage in swarm engineering where we can design algorithms, either bio-inspired or automatically, and we can design new hardware, either more sophisticated or simpler like these coin robots. And so our push now is towards making robots that work outside of the lab, or swarms for people. And part of that is obviously doing activities like this, more science engagements, so that we can tell the story of swarms, but also listen to what people think swarms can do for them. And one of our fun activities was to design an escape room called Swarm Escape, where we locked people in this little tent for 40 minutes or so, taught them about swarm robotics, had them crack lots of little puzzles to escape a chemical plume in the city. That was the storyline. And then at the end of that, we asked them what they thought swarms should be used for. And this is the plot of the Post-it notes that they gave us. And there's many areas that we find interesting in the field, such as search and rescue, cleaning the ocean of plastic, agriculture, inspection of infrastructure, massages. I thought massages, but actually now we have a PhD project working on massages, so who knows? So lots of areas where swarms could make sense in the future. And in fact, we have a roadmap in swarm robotics of where we think this technology is going, written by some of the core people within our discipline. And so to give you a sense of where we're going, 2020 to 2030, we're looking at first applications of robot swarms in precision agriculture and infrastructure inspection. 2025 to 2030, deployment of robot swarms for maritime and deep sea applications. 2025 to 2035, the entertainment sector uses robot swarms for interactive and immersive displays, and robot swarms are employed within the city, sharing the environment with operators and citizens, and they might be insect-like or pet-like and collaborate to carry out a number of service tasks. 2030 to 2040, first space exploration mission on the moon and on Mars, and these swarms could be used to explore or to build structures. 2030 to 2045, now we have tiny robots, millimeter-scale soft-bodied swarms that could be used for pest control in agriculture or to clean the ocean of plastics. And 2035 and 2050, microscopic robot swarms in medical applications in the body. And why do we think these applications make sense, whether it's medical, whether it's monitoring the environment for wildfires, construction, agriculture, logistics, or indeed space applications? Well, it has to do with the scale. So many of these applications you just can't tackle with a single robot, however capable that robot is. And so we're increasingly thinking about, well, if we actually want to make a difference, we're going to need lots of these robots. And in many cases, we're going to need many of these robots to coordinate in these challenging environments. So what I'm going to do now is walk you through some of the real-world applications of swarm robotics that we've been working on, and then figuring out how we aim to make these systems more trustworthy. At the nanoscale, we've been thinking about how we can design nanoparticles to treat cancer. And in particular, nanoparticles, because of their size, they're interesting as vehicles to deliver diagnostics or treatments to tumor tissues because they have the ability to leak out into certain types of tumors. And these nanoparticles work in the 10 to the power 13, so much bigger than the 10 flying robots that you saw at the start. And how we program these robots is very different from the way I programmed those flying robots. It's by changing the design of the nanoparticle. These particles come in different sizes. You can change their shape. You can change their material. Some of these materials are energy receptive, so you can use light or magnetic fields to activate them. You can decorate the particle with molecules that allow them to interact with certain cancer cells, and you can load them with a drug that you can release in a more or less controlled fashion. And at the laboratory of Sangeeta Bhatia at MIT, where I used to work, she was able to make a number of these nanoparticles. And so the way you program them is by turning the knob on the design of the particle, so the shape, the size, the material, the coating, the loading, and that changes what 10 to the power 13 nanoparticles do within a tumor environment. As an example, if you were to just turn two knobs, change the size of a particle, big particles are slower than small particles, and change the stickiness of the particle to the surface of the cancer cell, you would distribute in very different ways in the tumor. So imagine them leaking out of the vessel, and their goal is to kill 20 cells deep within that tumor tissue. Turns out that changing those two parameters sometimes leads to just killing the first cells right after the vessels, sometimes distributing really well over the tumor tissue, but this collective behavior really matters. And in fact, it's sometimes counterintuitive. So the bioengineers who were designing the sticky particles were very happy because in a dish in the lab, it would stick to all the cancer cells and kill them very well. But in these nanoparticle models, when they leak out of the vessel, they all stick very well indeed, but only to the first cell and never go deep into the tumor tissue. So that idea of a single particle working well, but the collective being very poor, is something that's useful to understand. And again, to automatically design these nanoparticle systems, to automatically design these nanoparticles, we use artificial evolution, growing virtual tumors, slicing them up into little virtual scenarios, and using evolution to turn the knob on the design of these nanoparticles, testing them in these virtual tumor environments to optimize delivery. And thinking of systems in swarms works in many different ways in biomedical applications. So if you're thinking of nanoparticles moving through the body and arriving at a tumor, you can also think of the reverse, thinking of biomarkers in brain tumors coming into the bloodstream and how much would you have in the blood. And it's very similar models that work for that. Or thinking of antibiotics and how they might treat biofilms towards treating antimicrobial resistance. At the microscale, we're looking at cells, artificial cells or engineered cells, and trying to control the collective behavior of these microscopic agents. How do we do that? We do that using light. And so we've created this device. It's all open hardware. If you want to make your own, you're welcome to. It's actually not very expensive to do. And this dome for dynamic optical microenvironment, what it does is blast thousands of pixels of light, and we can change what light we use, and it blasts that on our microswarms, and we can observe what happens to the microswarms, and then based on that, we can change the light that we project onto the system. So as a proof of concept, here you're looking at real algae called volvox. So what you see moving here are little algae. And you're looking at us using light to do different things. On the left, we're giving these algae the ability to communicate using light by projecting little halos around them. And we can change the light patterns, we can change how far they communicate. In the middle, the volvox are depositing light patterns in the environment. And it turns out that volvox react to light, so now they're actually messing with each other's behavior. And on the right, we're zapping them. And it turns out if you zap the volvox at just the right rate, you can stop them and you can control their motion. But it turns out, as we learned, that every volvox is different, so we also use machine learning to tune the light for every individual algae. On the biomedical side, we're thinking of using this for wound healing, so controlling the swarm of cells, in this case in the wound, to help drive the wound healing closure. And we do this using a new version of the dome called the LumiDome, and it's living in an incubator here because we put lots of little cells in it. So it's very slow, so it might take a little bit of time to observe what's happening. But this is a scratch wound in a dish, and you can see in the upper right this light pattern. We're zapping the leading edge of that wound, and it turns out that if you zap those cells and damage them just enough, that helps drive the wound healing process. So we're exploring how we control swarms of skin cells for biomedical applications. So if you're wondering where the robots are, I am getting back to it. And so now at the macro scale, we have many other applications. One of them is making robots that behave in a social setting with humans. So these are the tiles. We have 100 of these robots. They're basically screens on wheels, many components that you can buy off the shelf for those who are keen on making their own robots. That's something that you could build as well. And we've used them as puzzles to have people and robots together solve images and puzzles. We've used them in shopping malls to ask people about climate change, and they enter their opinion on what we could do to help fight climate change on the screens. And these robots then serve as physical avatars for their opinions once they've left and that travel within that environment. So that's been quite useful just in terms of engaging people, but also thinking about new decision dynamics between people and robots. And we've used them as little pixels that people can control. More recently, we used them in Bristol City, also to engage people on what the city should be doing to fight climate change. And in this context, they were smart Post-it notes, so people could come and write whatever idea they had on the screen of our robot. And then just like you would in a brainstorming session, reorganize the Post-its based on topics. The robots self-organize themselves. And so you see islands of ideas and thoughts, and when new ideas come in, the islands reorganize. We're looking at what we can do to detect and mitigate wildfires before they grow out of control. This is a project that we've been working on for 5 years now. One aspect is, again, the algorithms. What rules do we put on these flying robots? And the robots that we have access to are designed by wind racers, and they're quite unusual in that they can travel 1,000 kilometers and they can carry over 100 kilos. And that means that now we can cover huge areas. So the algorithms that we're designing are on the scale of California, and it takes, you can see different patterns. So on the middle side, you can sort of see California cut up into different pieces with lawnmower patterns. So I think that's how people often think we would explore an environment with robot swarms. On the upper right is another one of our algorithms. Looks a bit more chaotic. It's actually directly inspired from what the birds do. So basically, we're pushing the robots away from each other. When they're in the right positions, they start spiraling. And that allows us with actually reasonable amounts of robots to cover 24/7 an area the size of California. And we have algorithms to detect the fires and then to swoop down and extinguish them. And these are trials that we've just run with wind racers. These are fires that have been extinguished by dropping water balloons, basically, on those fires within the environment. And a big piece of how do we deploy these robots in reality is working with the users. And so we've spoken to 50 firefighters around the world. And in fact, this drone is decorated with the Lancashire Fire and Rescue symbols because we've worked with them closely to understand what it would take for these firefighters, who actually are quite used to using drones within the firefighting practice, but they tend to be the small drones and they tend to only work for 30, 40 minutes, to embrace being a swarm operator. And what would that feel like? And it's been quite encouraging that, first of all, they're open and excited about it. Also, that they don't feel like they need to control every single robot, but they want to have good visibility of what those robots are doing, and that there's aspects where their expertise is key. So for example, they really want the robots that detect a fire not to extinguish it autonomously, but to relay that information back to the firefighters so that they can design the right drop line for the water in that environment. And in fact, that is the main thing we've added to the interface, is the ability of the firefighters to control how you tackle the fire within those environments. We're thinking of how to use them to understand wildlife. So these are robots that have been designed specifically to look basking sharks. They live on the surface, and then they have a telescopic pole with stereo imaging. And the reason the biologists were interested in that is they don't understand very well the structure of raker gills, and we thought that would be interesting to both understand the biology, but people are curious as to how they capture algae, microplanktons, and that are about the same size as microplastics. And so that might also give interesting ideas to material science about how we could design that. So here are some of the images that we took in our first trials. And this is 3 of the robots, sadly waiting, because no basking sharks came that day. So if you have any good way to go back into the field, we would love to put these out again to see what happens. So it's not always what you think when you go into the field. And then one area that we've been spending, I would say, the most of our time now is looking at how we can design robots for logistics. So you might think that robot swarms for logistics is solved. If you look at big companies like Amazon, like Ocado, they have hundreds or sometimes even thousands of robots within their warehouses. And we've been looking at it from a different angle. In particular, what happens to the messy places? What happens in areas of small retail, pop-up warehouses, areas that we want to have reconfigurable? And indeed, what we're thinking is that robot swarms have the potential to be used out of the box within these messy environments where we haven't pre-installed infrastructure, where you haven't spent a lot of money in R&D to make the perfect robot for your environment. And why do we think that's the case? So let me just walk you through a thought experiment. Let's say you arrived with your jacket here and put it in a cloakroom, and your cloakroom was manned by a robot swarm. You could design that in 2 ways. If you designed it in the classical way, that would be a very centralized system. How would it work? You would arrive with your robots in the cloakroom. You would create a map of that cloakroom. You would take your robots out and put a big computer in the center, and then people would arrive with their jacket to the central computer, and the computer would say, okay, robot 1, 2, 3, follow this perfect trajectory, pick up the jacket, robot 1, 2, 3, follow this perfect trajectory, store it in a location. That would end up in a database. And at the end of the day, when you arrive to pick up your jacket, that central computer would again manage this whole dance. Now that can work, but you needed to map the environment. You needed really good communication across your system. You needed your database to always be correct, because if it moved, you won't find your jacket at the end of the day. And it required that central computer to always work. So that can work in well-structured environments. Let's say I arrived with a swarm. The way I would set that up is I would put a line on the floor to show the limits of the cloakroom. I would take my robots out of the box. And then these robots, if you come with a little phone and a Bluetooth app, you would say, hey, I have a jacket. And a nearby robot would come to you. You'd put your jacket on that robot. It would move around, deposit it anywhere in the cloakroom environment. And at the end of the day, you would arrive somewhere on the edge of the cloakroom and ask for your jacket. And all the robots would look around a little bit like what humans do, and they would find your jacket and bring it back to you. In that context, there was no need for global communication. There was no need for a map. There was no database, because it's always real-time search, given the number of robots in that environment. And there was no central point of failure, so you could add robots or remove them from that cloakroom, and the system would still continue to operate. Now, what it does require to design such a swarm is a new kind of robot. And so we've been building over the past 5 years a robot called the DOTS, for Distributed Organization and Transport System. And these robots are more sophisticated than the ones you've seen so far, in that they can sense much better. So they have 4 cameras, they have laser scanners, They have a GPU, they have 6 CPUs, they have a good battery, they can operate for 8 hours. They're quite fast, actually, they're driven by drone motors, and they have a lifting platform. So this remains a research platform, but it's now giving us the capability to really operate in an autonomous way, just perceiving the world around us. So now what you're seeing is these robots in the arena. They're behaving quite randomly, but very rapidly they can find those carriers and bring them back to the deposit area. Now the randomness bothers people, and it's quite fun because randomness works very fast and it's sometimes very efficient if you have lots of robots, but people like to know that the robots understand the world around them a little bit better. And so what we've been developing is what we call distributed spatial awareness, to allow the robots to figure out where they are, or it could be other information, but to share just information through local exchanges and to aggregate that in a way that they start to get awareness about the space around them. In particular, they're trying to figure out where the center, a common center of the world. It doesn't need to be the center of the world, but they're trying to come up with a common center of the world. And if they have that, it's almost like having position. And so that allows them to create maps of where the boxes are, which would allow them to go to there, or to do other swarm behaviors that are typically challenging, like pattern formation, just by using these local, simple exchanges of information. So robots are becoming more capable. And one question that we have is, what will this look like within our communities? And so we've been working with the Center for Socio-Digital Futures to ask what might swarms look like from a socio-digital perspective. So if you think of these logistics robots, that could change the way you organize cities or the way you exchange goods. Perhaps your city has, small retail shops that can quickly send things to their local environment, or maybe within a neighborhood you swap things more readily or share food or share tools in a different way if you have the ability to very quickly call a robot and that robot brings that item where it needs to go. Maybe we can organize things differently by having communal warehouses. So all these questions about what the future looks like given these technologies are things that we're curious about. And you could really imagine a variety of these types of delivery services. I think if you look at the news now, people think it's going to be the upper left corner here, but actually it could be anything in terms of how we design them. We might have one robot amongst humans. We might have little squirrel robots that scurry up trees and sort of hide there out of sight until they're needed. We might have things that look a little bit closer to little carriers on wheels, or maybe we'll have more the humanoid form. And I think understanding what these robots feel like, what they do, and how they integrate with our society is going to be important going forward. What's clear, however, is we're going to need to figure out how to make these systems trustworthy. And that's something that we've just scratched the surface of. One thing we've wondered is, how do we go about making these swarms safe? So we could look, is this an ethical swarm? Is it operating in the legal context? How do we prevent harm from the individuals in that swarm, but also from the collective behavior of that swarm? How do we prevent that system from being hackable? So all these questions are things where we need new tools. And in fact, we probably need new governance frameworks for swarms in the real world. And so we've been working on this with Alan Winfield, who's an expert in roboethics, considering different use cases such as city-scale logistics, fighting wildfires, monitoring the environment, or fighting cancer at the nanoscale. We've also been looking at what impacts trust in these systems, and there's much more than this, but these are some of them. One is the fundamental swarm properties. So our hope is that swarms are quite good at what they do, and that they're robust, and that they're scalable, and they're adaptable. So that might sound great, right? If your system can scale, you can have lots of robots and it still works. But having lots of robots, does that make it less trustworthy or more? Because all of a sudden you can't manage all those robots. The fact that it can easily adapt to changes in the environment might sound great because it still works. It's still good at doing what it was meant to do. But the fact that it changes behavior, does that make it less trustworthy or more trustworthy? We just don't know. The fact that it's robust to failure, you might think wonderful, right? Your system works even when robots fail, and so it's good at doing what it's meant to do. But robots are failing, and will people trust the system as a result of that? They don't always fail. But that's something that we just don't know. We don't know if the properties inherent to swarming are things that people are happy to trust because it works, or that bother them because they're used to a different kind of engineered system. Beyond the swarm properties, we're interested in how humans and swarms might interact in the future. And in particular, how can they easily program the swarm to do what they want them to do? And in one of our pieces of work, we let people decide what they think makes the system trustworthy, so they can prioritize safety of the swarm, performance of the swarm, robustness of the swarm, or its energy use. And so different people might have different preferences. But these are all trade-offs. So you can imagine if you want your swarm cloakroom to be safe, well, it might be very slow. And as a result of that, it might not be as good in terms of its performance. And so you can't get everything. So what we've designed is a tool that uses, again, artificial evolution, but instead of giving the best program, it gives all the trade-offs. So you as the human operator can look at different options and pick the one that work best for your preferences. We've also been wondering if people are happy with the system being messy. And so we had a human trial with people coming to the lab using our robot cloakroom. So they deposit their own object, it could be a phone, it could be anything else, and they store it in that cloakroom, they go for a coffee and come back and retrieve their item. And on the left, there was organic motion, and on the right, structured motion. What does that mean? You probably didn't even notice. Structured motion was that they operated in a very angular way, the way you think robots should behave. And on the left, they would zigzag, they would stop in random places, but the performance in both cases was exactly the same. So if you wanted to retrieve your phone, you didn't see a time difference. And we were worried that the messiness would bother people, but it doesn't seem to bother them, actually, as long as the performance is good enough. So we're trying to understand what people are happy to accept when you put these systems out in reality. Another area we're curious about is people wondered if emergent properties of swarms could be validated in the same way as you would validate the fact that your airplane is properly designed. And so we've been working on a new framework with Kristen Etter's team on swarm specification, verification, and validation so that we can test these swarms before they're deployed in reality. And the challenge is that we need to test the emergent properties of the swarm, not just the behavior of the individual robots. For example, for specification, you can write down all the things that you think your swarm should do, and in particular, its emergent properties. Once you've written down those specifications, that gives you something that you can test. So for example, I've learned since living in the UK that people really care about fire exits. And so what we said is our swarm as a whole should not block the fire exit. And the fire exit happens to be in that red corner in the upper left. So first of all, that is a swarm property. You need multiple of them to really be blocking that area. Then we did formal verification. That means basically we did maths to verify some properties. Then we simulated it very, very fast over thousands of trials in low fidelity. So these are simple simulators that are fast. Then we simulated it in more realistic simulators that capture the physics, but we can't do as many tests. And then we try it in our real arena. And through this process, we had identified that these fire exits would probably be blocked by 2 or so of those at a single time. And that was verified in reality and teaches us something that we need to improve in our system going forward. And even though they're robust to failure swarms, we realize that that's not always the case. And so we also need to find ways to fix swarms or detect that they're faulty and fix them on the go. So what you're seeing here is a swarm of robots trying to carry a big box. They need 4 robots to carry the box, and the red robots are faulty. And as you can see, they're not carrying that big box. So those are critical faults which prevent the swarm as a whole from doing their job. But again, using learning, we can come up with better mitigation strategies. So here you can see these red robots have actually detected their fault just by looking around them. So they don't need any central computer. They figured that out on their own. And they figured out that if they go to the side of the arena, they won't be tempted to pick up that box. And as a result, the robots, even though they're a bit slower, are able to complete their task. So we are on a journey towards the future, and this is what I think we have the potential to achieve with robot swarms, although you saw the timeline is going to take us a little bit of time. But it's also going to take us a bit of a paradigm shift. So this is the definition from 20 years ago for swarm robotics. And that's driven a lot of the beautiful science that has happened over these 2 decades. So swarm robotics is the study of how large numbers of relatively simple, physically embodied agents can be designed such that a desired collective behavior emerges from the local interactions amongst agents and between the agents and the environment. The things that are really important in that definition have been that the robots should be autonomous, that there should be large numbers of robots, that they should be homogeneous, that means all the robots are the same, and that they should be quite incapable or inefficient individually. And what we did this year, actually it was last year, now we're in 2025, so what we did last year was to really ask ourselves, is that what's going to enable those real-world applications? And we had a workshop with the people from the swarm community on breaking these stereotypes, and we've relaxed them. So for example, should our swarms really be autonomous? Well, probably they need human collaboration and human input and the ability for humans to control and monitor them. Should we have large numbers of these robots? Well, that really depends on the applications. And sometimes those swarms will be sparse or spread out. So for example, on the picture of the algorithm for the swarms of flying robots, that looked really packed, right, with all those spirals. But that was over 600 kilometers by 600 kilometers. If you were to look in the sky, you would probably only see one of those robots, if at all. And so even though they're operating through swarm algorithms, they're much more spread out than those coin-sized robots you saw in my lab. The fact that they should be incapable or inefficient has also been relaxed. And actually, a lot of the biological systems we take inspiration from are very capable. They really understand their local environment. They're able to do things individually that we can't even do with our robots. But in the future, and increasingly so also with the advent of these large language models, our robots, even with cheap hardware, even with cheap sensors, are going to be much more capable at understanding the local world around them. We've always been about designing swarms in a very local way, just using these simple rules. But increasingly, we're also thinking about some of the information that we should be sharing more globally through the cloud or other infrastructure. And although our systems are emergent, we're trying to think of them as an engineered system so that we can verify them, validate them, and build them in a way that can be trusted. Because in the future, I think it's not just one swarm for one application, but it's going to be a mix of these swarms in different environments. And these swarms are going to be heterogeneous, and they'll need to understand what their role is. They'll need to be able to communicate that with users or other robots in that system. Different types of robots will coexist in different spaces. And so it'll be important that we understand how to design these in a way that's responsible. So a lot of this is driven by humans. You might not believe that. And so what's been really fun as well is in the field of swarm robotics, we come from many different disciplines. So this is the swarm behind the swarm. And they come from biology, from machine learning, computer science, biology, robotics, social science, and AI. And I think this is something that's really helped us think beyond those little robots that we had in the lab. Right. Thank you very much.